So for the next part of the unit, what we're going to be doing is we're going to take expressions that are in trig and we're going to simplify them. So this right here has all of the basically like legal substitutions, like legal math substitutions you can make with something. So these are called the reciprocal identities. This is what we talked about before, is that if you want to find sine or cosecant of something in your calculator, you would do 1 divided by sine. So cosecant is 1 divided by sine, sine is 1 divided by cosecant. So these are the reciprocal identities. You have to memorize these. These should be in your brains. Okay. Quotient identities. Tan is sine over cos. You guys already know that. But cotangent is cos over sine. You also need to memorize that. Okay. So I'm going to maybe put stars next to things we have to memorize. We're going to memorize the reciprocal identities. We're going to memorize the quotient identities. The even and odd identities. Do you guys remember that we found even and odd back in the day? Well, not back in the day. It was this year. We plugged in negative x, and if it gave us the original function, then it was even. If when you plugged in negative x, it gave you the opposite sign, then it was odd. So that means that this right here, sine is an odd function, cosine is an even function, tan is an odd function, cosecant is an odd function, secant is an even function, cotangent is an odd function. So these don't, technically you'd have to memorize them, but they don't get used very often, so you don't really have to memorize them. Same thing with the cofunction identities we typically, so I put them on here because when you look up trig identities, you'll see them, but we don't necessarily use them a lot. All right. The Pythagorean identities, this is the one that you have to memorize, that you're going to have to train yourself to memorize. The other ones you'll probably memorize by default. These ones you're going to have to watch out for. Okay. You'll memorize them eventually, but maybe not as soon as you need to memorize them. So those you're going to have to actually work for. When we get to the test for this, I will give you a little resource page on the test that has these 3 on it: sum and difference, double and half angle. All of these will be on a resource page. The rest of them I expect you to have memorized. Does that make sense? Okay. So just to clarify, probably don't have to memorize these 2 just because they don't show up very often. These 3 I will give to you when you take a test. The ones with stars you definitely need to have in your brain because they're very basic. Okay? Reciprocal, these ones. You learned these, that cosecant is 1 over sine, secant is 1 over cos. You learned that before, so now it's just saying that the other version is true as well. Okay. All right, does that make sense? You can see what we have to memorize, what we're going to have? Okay. So on your notes, the title of your notes are going to be Simplifying Trig Expressions. And this is what I was talking about when I said that things get to be a little bit more difficult. The reason that I said that is you can't just memorize how these problems go. There's not a set pattern. They do not work the same every time. You have to actually understand what you're doing and look for clues. You get to the point where it's almost like playing a game where there's some strategies that seem to work, but they don't always work. Have you guys noticed that in games? Like when you're playing Monopoly or something, there are some strategies that might be helpful, but maybe you don't always win if you use your strategy. That's kind of how these problems are. There are some strategies that often work, but they don't always work. Okay? So the best way to get good at these problems is to do a lot of them. When I first start doing them, you'll probably be like, Ms. Rice, it makes sense when you do it, but I would never see that. And I'm like, I get it. I know the way that you have to make it so your brain can start to see it is by doing lots and lots and lots of them. That makes sense? Okay? So if you do not do lots of homework problems for these, you will not be able to pass the test. I can guarantee it. You have to do lots and lots of practice. You understand? Lots of practice? Okay. So what I'm going to do is I'm going to go through some example problems, and we're going to use our green sheet, and then I'm going to give you guys some strategies that I've picked up as I've done these problems for years. Okay? So here is our first example problem. We are going to simplify And our expression is 1 plus tangent squared x divided by cosecant squared x. We're going to actually, I'm just going to write like this. We're going to simplify that. Okay. Now, these problems get really messy really fast. So what I say is I like it if you do your work vertically. So we put one step, we'll put the next step underneath it, the next step underneath that, the next step underneath that, and we will not try to conserve paper. You will take up space. If I don't give you enough space on a worksheet, then you should do it on a separate sheet of paper and kill all the trees this unit. Okay? All right. So what I'm going to do is I'm going to look on my green sheet, and typically one of the strategies that I say is if something is squared in the problem, then you should look at your Pythagorean identities because that's where the squared things show up. Okay? So basically what we want to do as we're simplifying these is we want to make a substitution. So I'm going to take something and substitute it with something else, and then I'm going to simplify. Okay? So we substitute and simplify, substitute and simplify. And by simplify, that might be like cancel out things that multiply and divide. It could be simplifying by getting a common denominator. It could be adding things together, combining like terms. Just any sort of simplifying that we've ever learned in math, our entire math history. Okay? So with this, do you see anything we could replace? Yeah, do you see? So if we look at the top, it says 1 plus tan squared, right? And right here we have 1 plus tan squared. You guys see that? Mm-hmm. So typically what we want to do is we want to take something that's complicated and make it a little bit more simple. So I'm going to take that 1 plus tan squared, I'm going to simplify it and take out the 1 plus tan squared and replace it with secant squared. So I have secant squared divided by cosecant squared. Okay? So I made a substitution. Okay. When I look at that now, is there anything that could cancel, anything that could add or subtract, anything, any common denominators, any of that? Now, can your x's cancel? No. Because if you say secant of something, cosecant of something, can we cancel the thing that we're doing cosecant of? No, because I'd be like, oh, now my problem is just divide by divide, and I'm done. Does that make sense? We gotta have something that we're like dividing with, or something that we're doing secant of. So that was all that we could do for that. Okay. Now at this point, it does not make sense for me to use these Pythagorean identities because I'd just be switching back and forth between the two of them. Okay. So now we're going to look over here at these reciprocal identities because we have cosecant and we have secant. So cosecant squared is one of the things that we have. And this just says cosecant is 1 over sine. So if we have cosecant squared, then cosecant squared would be 1 over sine squared. It would be like you took this and multiplied it by itself. So cosecant times cosecant would be 1 over sine times 1 over sine. So I'm going to take the cosecant squared, and I'm going to replace it with 1 over sine squared. And what should we replace the secant squared with? 1 over cos squared. Yep. So secant times secant would be 1 over cos times 1 over cos. So that's 1 over cos squared. So if you're paying attention to what we did, we started off with the original problem, and then we made one substitution. We substituted out the top for something else. And then after that, we made 2 substitutions. We substituted the top out for something, and we substituted the bottom out for something. Okay? Is there anything we can simplify? So no substitutions, just is there math that we know how to do? Yeah?
Well, you could multiply by the reciprocal, so you can sine square everything.
Yeah. So we can keep it, change it, flip it, right? That's what she meant by multiply by the reciprocal. So I'm going to say keep it, yep, change it, flip it, which is multiplying by the reciprocal. So if I have 1 over cos squared times sine squared, then what does that give me? Over that. Yeah, sine squared over cos squared. Okay, so say it again.
Can you get rid of the squared?
You can't.
Oops, I didn't do that.
So sine squared over cos squared. So this means we have sine times sine over cos times cos. So if you look at your sheet, what do we know about sine divided by cos? It's tangent, right? So if I have sine over cos and another sine over cos, because I have sine squared, right? So I have two sines on the top and two coses on the bottom. What does that give me? Tan squared. So this problem, when I simplify it and I'm all done, it equals tan squared x. And it's simplified because the original problem said 1 plus tan squared divided by cosecant squared. But the end result was that it was just tan squared, so we simplified it. Okay? All right. So do you guys see what I'm saying about how this is not a process we can memorize? Okay? I think we can maybe think a little bit creatively and realize that all these problems are kind of going to look like way different. Okay? So what did we refer to multiple times? The green sheet, okay? The strategy is going to involve how you make your substitutions, okay? The strategy also involves how comfortable you are with algebra. Are you comfortable adding fractions? You have to be. You have to be comfortable adding fractions to do these problems. Do you know when things can cancel? For instance, if you had canceled the x's, you would have been done. Like you would have messed up the problem from then on. Does that make sense? Okay? The thing that messes with people is that these problems can be done a ton of different ways. So we could have done the problem with a different first step, and maybe we got to the final answer, but instead of taking 1, 2, 3, 4, 5 steps, we took 17 steps, but we still got to the same answer. So when you use your strategies, some strategies make the problem way harder, but you can still get there. Does that make sense? Okay, so we're going to do another example so you can start to see. All right, example 2. Cos x minus cos to the third x. So cos minus cos cubed. All right, does it make you think of anything right now? Not difference of cubes. Almost Pythagorean identities. It's not a Pythagorean identity yet because we don't have a squared term. It reminds me of the factoring assignment.
Oh shoot, can you take out a cos?
You can take out a cos. Do you guys see it? We could take out a cos? Yeah, it's a GCF. Okay, so I'm going to take out a cos. And when I take out a cos, what do I have left over?
X minus cos squared.
1 minus cos squared. Okay, so we did some math, right? We did some factoring. That's an algebra thing we know how to do. Now that there's no more algebra for us to do, now we look at our green sheet and see if there's any substitution we could make. Yeah. It's not an x, it's cos x is being multiplied by itself 3 times. So what this really means, and this might be good to put on your notes, this really means that cos of x is being cubed, right? Okay.
Wait, this price?
Yeah.
Can you do the Pythagorean identities into 1 minus?
Yeah, you can. So if you look on your green sheet has the original Pythagorean identity, which is sine squared plus cos squared equals 1. But then it has like the secondary, it has like the results of that, which is that 1 minus cos squared equals what? Sine squared. So we're going to replace the 1 minus cos squared with the sine squared. And then we are done. So when the first day that we do these, I just give you an expression. That means there's no equal sign, and you just simplify. You do as much as you can. The nice thing about this is we're going to end up doing what we call Trig Proofs, where there's one thing on the left side and one thing on the right side, and your goal is to show the steps that get you from the left side to the right side. So you would simplify until it looks like the right side. So the nice thing about this is that with these problems, you know what the answer is before you get started. I'm going to give you a worksheet today that has the answers on it, since we are eventually going to be doing proofs anyway, where we will already know the answer when we do it. So this process is less about getting the answer. It's more about doing the individual steps right, because when we do proofs, we're already going to know what the answer is. Does that make sense? Okay, so for today, I will always give you the answers. Okay. All right, example 3. Okay, example 3. Sine x times tan x plus cotangent x. I will say, though, I don't know how many of you guys kind of enjoy math because you kind of enjoy puzzles. I know that some of you guys don't like math. I kind of enjoy math because I like figuring things out. This is, without question, in all the years of math, this is one of my favorite things to do. Like, I love these problems because you know when you got the answer right, and it's really satisfying. It's like a puzzle. You can make, there's like rules to the game, but if you can figure out the rules, you can always get it. And they have some problems of these that are really intense. I will not give you the super crazy ones, but they have some that are really hard. This is something I would do for fun in my free time at a coffee shop. I know it's nerdy, I'm a math teacher, but I think these can be kind of enjoyable if you like understand what you're doing. Okay, so what we're going to do is we're going to start off by making some substitutions. Okay, so we're going to make substitutions for tangent and cotangent. And instead of turning them into each other, I'm not going to take tan and put it as 1 over cotangent and take cotangent and put it as 1 over tangent. I'm not going to do that because that makes it just as hard. I'm going to take tangent and I'm going to rewrite it as sine over cos. Okay? Yeah. So I went ahead and I made my substitution. Notice that I'm not ditching my x ever. I didn't write sine over cos. I wrote sine x over cos x. So as you're doing your steps, make sure you're always writing things correctly. Okay? So we're taking up space. We're working vertically. We're not worried about wasting paper necessarily today. Okay? Now, if I have a fraction and another fraction, what should I probably do? Common denominator. Common denominator. Does that make sense? Common denominator? Okay. So anytime we do these problems, we're just thinking algebra. What would algebra tell us to do? So if this one is cos and this one is sine, then what's our common denominator? Yeah, cos and sine, right? So this one has a cos, it needs a sine. This one has a sine, so it needs a cos. So I wrote down the inside of the parentheses with that common denominator. And what do I have on top?
Sine squared.
So sine squared plus cos squared. Okay. So we did, I can see there's some algebra I see that we could do. There's a substitution I could see that we could do. So does anyone see either one of those, a substitution or some simplifying? There is something you could divide. Anyone see it? It's not with a cos. You can't do anything with this sine squared. It has to do with this one. Okay, so I'm hearing a substitution. So sine squared plus cos squared equals 1. Okay, so we can make that substitution. We'll leave the algebra for a second. So 1 over cos x sine x. Okay, can anyone see?
Can't you take the sine out?
Yeah, you can divide the sine. Sine divided by sine, those cancel. Do you see that? So this is sine times something. This is a sign that's being divided.
That's over 1 and then just cancel.
Yeah, so it's kind of like this is over 1.
Oh, it's just secant.
Yeah, so sine and sine cancel. That's an algebra substitution we can make, or an algebra simplification. Now we have 1 over cos, which is secant.
The x, is that cos theta?
Yeah. So sometimes they'll say sine x, sometimes they'll say sine theta, sometimes they'll say sine beta, which is a Greek B. We'll start to get more Greek letters in this.
It all means the same thing.
It's just representing whatever angle you're doing the sine of or whatever. Okay? We're going to do another example. All right, we're going to do sine times cos times tan times secant times cosecant.
How long is it if we miss an X like on the problem? Like, how many
If you miss one here and there, I would probably ignore it. If you don't put 1 X on your entire paper, I'm going to be so mad. And baby animals are going to die. I'll start calling you Ector. Because some letters just aren't important. All right. So if we look at this problem, there's not really any algebra we can do, right? Like there's no like terms to add or anything like that. So we go straight to substitutions. Anyone see a substitution we can make? Well, think about your sheet. Should we be looking at the Pythagorean identities?
No.
No, we shouldn't.
Reciprocal.
We can look at reciprocals.
Could you turn cosecant
Or
into
quotient.
over sine?
Okay, so we could turn cosecant into 1 over sine. What's this 1 over sine going to do? It's going to cancel with that one.
Oh, shoot!
Do you guys see that?
Oh, shoot!
Right.
So I'm going to write those both and say that we canceled both of those. So we've taken care of this part. What else do we want to do?
You can use secant.
Does the 1 cross
Okay,
out too?
secant, the 1, multiplying by 1 doesn't really do anything for you. So we're going to leave it there, but when we multiply by 1, it's... Yeah, so we drop down the cos, and then we know that the cos x and the 1 over cos, those cancel. And then I don't really need to change the tan, right? And so my answer is tan. If you changed the tan, you might have changed it to sine over cosine. And then when it didn't cancel, you'd be like, well, it's simpler if I leave it as just tan. Okay. All right, are we seeing how it kind of feels like a puzzle?
Yeah.
No.
So these, I really enjoy these. Okay, we're going to talk some strategies, all right? And as we go throughout this over the next couple days, we'll start to look for more strategies because there are some strategies that I saw the first year that I did this. And now that I've been teaching for 10 years, there are some strategies I'm just now starting to pick up, but my students told me about last year. Like some people just see it a certain way and they pick up different strategies, okay? So one strategy that I have is I look for a relationship. And what I mean by that is that I was like, why are they all giggling? What I mean by that is that sine and cosecant have a direct relationship. You can switch them from one to the other. Does that make sense?
Yes.
Cosecant and secant have a direct relationship. You can trade them one to the other. Tan and cotangent, they have a direct relationship. You can trade it from one to the other. The Pythagorean identities are kind of interesting because the Pythagorean identities, they make it so that if you have a sine squared and a cos squared, you can trade them out. Does that make sense? So not only does sine and cosecant have a direct relationship, but sine squared and cos squared have a direct relationship. Does that make sense? Now, people always say, Ms. Rice, if sine squared plus cos squared equals 1, can I then say sine plus cos equals 1? The answer is no. to use the Pythagorean identities, you have to have a squared term. Does that make sense? Okay. Now, the other thing is that even though secant and cos have a direct relationship and tan and cotangent have a direct relationship, the Pythagorean identity tells us that secant squared and tangent squared have a direct relationship. Does that make sense? So when I approach a problem, I say, like, what different trig functions are here, and can I relate that back to what's on my green sheet? Is there a relationship here that maybe if I switch one thing, then that direct relationship on my green sheet is going to show up? Okay? So look for a relationship is the first one. The second one is if it's squared, look at the Pythagorean identities. If a term is squared, look at the Pythagorean identities. Okay. Another strategy, this is something that you are probably going to hate, but it comes up all the time. If you have two fractions, get a common denominator. It is very, very common in these problems to add or subtract fractions, getting a common denominator. Okay? Or like that problem where we had a fraction over a fraction, we did keep it, change it, flip it. That happens all the time in these problems. Okay? Lots and lots of fractions, which if you look at your green sheet makes sense, because what do you see a bunch in the upper right corner of your green sheet? Fractions. So these problems have lots of fractions. Okay? So if we're adding them, we're going to get a common denominator. If we have a fraction over a fraction, we're going to keep, change, flip. Okay? So get a common denominator, keep, change, flip. Those are things we're going to keep in mind when we see fractions. All right. It is typically good, not always, do not do this 100% of the time, but it is often good to get the problem in terms of sine and cosine. So the reason that we often get the problem in terms of sine and cosine is because cosecant and secant go straight to sine or cosine. Sine squared and cosine squared go back and forth. And cotangent and tangent both can be in terms of sine and cosine. Does that make sense? So it's kind of like sine and cosine are like the major players of these games, where they end up like showing up a lot. It does not work 100% of the time, but it often works to turn it in terms of sines and cosines. Does that make sense? Okay. I'm going to add one more thing. If it is only in terms of cotangent and tangent, do not use sine and cosine. So the reason why a problem that has only cotangent and tangent in it, the reason why we would not do sine and cosine is because those already have a direct relationship. Tangent and cotangent already go back and forth. Does that make sense? Okay, so I've seen a lot of students who are like, no, I'm always supposed to put it in terms of sine and cosine, and they end up doing a tan cotangent problem, and they make the problem so much harder because they made it in terms of sine and cosine. Okay, so we are going to add strategies to this list as we come up with them. So as we come across problems, we're just going to add to this more and more. Okay, it's not a list to memorize, and this is what I was saying is the only way to get good at them is just do a lot of them because you'll start to see it. Does that make sense? Okay, so I'm going to give you a worksheet. So we're going to practice some of our strategies. All right, so for number one, it says here they're using a t instead of an x or a theta. So we've got tan squared t plus 1 and 1 plus cotangent squared t. And based off the strategies, what do we think?
You don't use sine or cosine.
We're not going to use sine or cosine because tan and cotangent have a direct relationship. But that direct relationship is, we could do that direct relationship actually. We've got two options, okay? So if you look at your green sheet, we know that sine and cotangent and tangent can switch back and forth, right? So we could go that route. The other route is we could look at our Pythagorean identities.
Whichever one's shorter.
Because we have a squared term. I'm not going to tell you which one is shorter, you're going to have to figure it out. So if we look at our green sheet, I can see two ways of doing this. I see that I could use these two right here to go back and forth. Or I see that I could use 1 plus tan squared, 1 plus cotangent squared because I've got those Pythagorean identities. I'm not going to tell you which one's easier because you have to start to learn this. So which way would you guys rather do? The Pythagorean?
Yeah, the Pythagorean.
Okay. So tan squared plus 1, is that the same thing as 1 plus tan squared? No.
No.
When you add things, you can switch the order.
Yeah.
3 plus 5 and 5 plus 3 are the same, right? Okay. So you can switch the order when you add, that's okay. So tan squared plus 1 should be replaced and become secant squared t. 1 plus cotangent squared is cosecant. Okay. There's no algebra we can do right now. We can't divide anything or add fractions or whatever. So what could we do? Reciprocals. So secant squared I'm going to rewrite as 1 over cos squared. And then cosecant squared is 1 over sine squared.
Miss Rice?
Yeah.
What are we switching between like t and theta and x? Like let's say this problem gave us t. What about use x?
You should use the same letter.
Oh shit, that's 10.
Because if you're telling me that letters are not important, then I can call you sector, and that's the same as hector. Because letters aren't important. You know what I'm saying? Alright, so what are we going to do now? Keep it, change it, flip it, right? So I'll go ahead and just flip this one up. Sine squared t over 1. So if I have 1 over cos multiplied by sine over 1, well, 1 over cos squared multiplied by sine squared over 1, what does that give me altogether? Sine squared over cos squared, which we already know is going to become tan squared. Yeah. So this is kind of like one of our sample problems, right? Sine squared over cos squared is tan squared. Okay. All right, number 2, secant t minus tan t. Okay. We've got 2 different fractions. They are being subtracted. Say it again. Yeah, so you've got a couple options. I could see you getting a common denominator. I could see you taking the problem and turning it into sines and cosines. So would you guys rather do common denominator, or would you rather do sines and cosines? Sines and cosines? Okay. So if we do it in terms of sines and cosines, then with secant, what are we going to turn that into? 1 over cos. Okay, so I've got 1 on top. On the bottom, I've got 1 over cos minus, and what is tangent? Sine over cos minus 1 over cos t. plus sine over cos. Okay. What happens on the bottom of each of these?
Cos.
Yeah, we have that common denominator. You guys see it? Okay. So I'm going to rewrite this problem as 1 over, not cos squared because you don't multiply it. So we have 1 minus sine over the common denominator, like that. Minus 1 plus sine over the common denominator. So what should we do with each of these fractions? We can't subtract. Say again? Keep, change, flip. Keep, change, flip. So I'm going to flip it up. I'm going to flip it up. So that gives me cos t over 1 minus sine t. Cos t over 1 plus sine t. Did putting it in terms of sine and cosine help us avoid getting a common denominator? It sure did not. If you're going to need a common denominator, it's going to happen no matter what you do. Okay? So, it didn't mess up the problem. We can still do it. Was it the easiest way to do the problem? Probably not, but I let you do it anyway. We flipped them. We flipped them because we had 1 over a fraction, and the way that we handle that is by keep, change, flip. Okay. All right. Okay, so we need a common denominator. How are we going to do that?
Multiply.
Multiply
by what they need.
by what they need. Okay, so the first fraction is going to multiply by 1 plus sine t, and has to multiply by it on the top and the bottom. And the one on the right needs 1 minus sine t. Okay. So on the top, we have cos times 1, which is cos t. We have cos times sine, which is cos sine. So plus cos t sine t.
Why would they choose T?
I don't know. I think the whole worksheet's t, though, so you're going to have to feel good about it. All right. Minus, and now I got to put this stuff in parentheses. So the thing that messes students up is that we're using the algebra that we've learned our entire lives, and some students will start to make mistakes with the algebra they've always done. So we know that anytime we subtract off more than one thing, we need it to be in parentheses to make sure we distribute our negative. Okay? If I do cos times 1, what do I get? Cos. If I do cos times negative sine, what do I get? Negative cos t sine t. Okay? And what happens on the bottom if I do 1 plus t times 1, or sorry, 1 plus sine t times 1 minus sine t? I have to FOIL it. Now remember I said, any algebra you've learned before is fair game. When you first start doing these problems, it's like when you first start working with a cell phone, like a brand new cell phone you've never had before. Everything is difficult at first, and then what happens? You get the hang of it. You get used to it. So foiling this out right now is going to be annoying, but the next time you see it, you're going to recognize it. Does that make sense? Okay, so I'm going to write 1 plus sine, 1 minus sine, and I just know that I'm going to have to FOIL that in a second.
Or
All right, so on the top, we have cos t plus cos t sine t. minus cos t. Do you guys see it? Minus cos t. And then plus cos t sine t.
So this time we're not using some of them.
Yeah, do you guys see what cancels on the top?
Yeah.
The cos, the plain old cos cancels. Okay. Let's go ahead and FOIL the bottom. So we have 1 times 1 is 1. 1 times 1 is 1. 1 times negative sign is negative sign. Sine times 1 plus sign. And then positive sign times negative sign. Negative sign squared t. Okay, do we see anything that cancels out there? The signs, right? Negative sign and positive sign. Okay, so we have 1 cos t and 1 cos t sine t and another cos t sine t. That means that we have 2 of them. So I'm going to say we have 2 cos t sine t's. And on the bottom, we have 1 minus sine squared t. I cannot cancel out signs because I would kill a cow. But if we look at our green sheet, yeah, 1 minus sine squared is cos squared. All right, so I'm going to leave the top the same, and I'm going to replace the bottom with cos squared t. Sorry. Okay, we've got algebra to do. We're not done. Yeah, you have a cos on the top, and you have a cos times cos on the bottom. So 1 cos on the top can cancel with 1 cos on the bottom.
Can I have 2 sine t over cos t?
And sine t over cos t is tan. It's 2 tan t, and we're done.
Oh.
Raise your hand if you make the bottom of your paper.
Yeah.
You did like 6 steps. When you could have done like 5 steps.
There's no shortcuts in life. Period.
Okay. Now, are they always that long? No.
Yeah.
The problem, are you listening? The problem probably would have been easier to do with the Pythagorean identity and use get a common denominator right from the beginning. And the reason, are you listening? The reason is if you got a common denominator right from the beginning, you would have had secant squareds and tan squareds. And if you look at your Pythagorean identities, secant squared and tan squared work really nicely together. That would have made the problem a lot easier. So that's kind of what I was talking about, where we say that getting it in terms of sine and cosine is definitely possible, but doesn't necessarily make it easier. Does that make sense? So when you do the problems, you don't look at the whole thing all at once, because that's overwhelming. You look at just one step at a time. And you say, can I make a substitution using my green sheet? Or should I be doing some algebra to simplify? Does that make sense? Okay. Now you have to practice on your own, because me doing it up here isn't going to help you that much. Okay? Ready? Break.
Can I go to the restroom?
Yep.